The assignments will be available online very late today or tomorrow morning. I'm finalizing at the moment, but at the end of this lecture, because the lecture is fairly short, I'll go through the assignment very briefly as to what tasks you have to do. And because it's a bit later than I thought, the assignment will be due on Friday, week 12, instead of Monday, week 12. More details at the end of the lecture. So, at the end of last lecture, I promised I'll recover this portion, which is a bit more complicated, so I'll revisit linearization. If you recall, we had a thing called least squares linear regression, or least squares fitting, that fitted a straight line to a data point by minimizing the residual that direction. And you can also do an R squared coefficient of determination, which compares it with a fit like so, like a mean. Okay. Now the problem with that was that you couldn't fit anything that's not a straight line. So to get around that, you can linearize certain kinds of equations. I mentioned power, which was the b squared version we had last time. You can also do exponential, and both of them use log on both sides to do that. Saturation growth rate we'll cover a bit of today, and it's used to model a lot of things that grow but then asymptote to a fixed value. So how they did that, I will just quickly show you the derivation. It's fairly straightforward. So if you have an equation like that, so I've replaced the alpha and basis with a and b to make it a bit easier to read. You have something, like so, b, and you effectively flip both sides. You divide both sides by, you flip it the other way around, you have something like so, okay? Now that's almost the right form already. What you then do is you take those two as a denominator for everything, and you end up having something along these lines. You have this, and then you have something like that. Now this cancels out, but that becomes your final model. 1 over y equals 1 over a, so that's your a0 part of it. And then if for this one, what has been done is you do it this way. You do it like so. Okay, so you break it up as b over a. Edge of the screen doesn't work. So it's effectively 1 over a plus b over a times 1 over x. So you can see that this is your usual y value. This is your a0. This is your a1. And 1 over x is your x value that you're using linear regression on. So that's how that linearization works. So it's just rearranging standard algebra. So that's what gives you this. And just to repeat, this is the y value, and this is the x value you use to fit a straight line. This is your a0 here, and this is your gradient a1 for the linearized version. So once you have done this, what you would do is then say, okay, I got an a0 value for that. I'll then divide it 1 over a0 to give me the actual alpha free value, okay, which you can then sub into the original equation. So that's linearization, and we covered that, and there was a log example. At the very end of last lecture, I also quickly showed you the polyfit and the polyval functions, which I again cover today. Polyfit is effectively a supersized version of your linear regression function. So if you put in a 1 here, it's fitting something in the form p1 x to the power of 1 plus p0 x to the power of 0, so nothing there. And it gives you back the p values as a vector. But if you increase it to above 1, which we'll show you this lecture, you can do x squared, x cubed, any polynomial function you want, so any order you want, and adjust the general form. So instead of using linear regression for the lecture, lab, and also the assignment, you are also allowed to use polyfit unless specified otherwise. And polyval is effectively subbing in this thing that you've got from polyfit with the x value, or a bunch of x values, so you don't have to sub it in by hand. Okay? So polyval is substituting it in to give you the straight line fit for any point. Okay, so that's end of last lecture. I'll go into lecture 16. So just make sure that you understand linear regression from last lecture and the linearization. So the very last model from last lecture was a saturation growth rate, SGR model, and that's often used for anything to do with chemical reactions, from biological chemical reactions to anything else like corrosion. The idea is that the curve kind of looks like some form like that, where there is an asymptote value it saturates on. But the way it grows is quite unusual. Okay? And for all these terms, they are just values. So your saturation, concentration, your substrate concentration is actually just one variable, even though there's strange square brackets there. And these are constants. You can treat them effectively. Okay? So this looks like the thing I just derived. It's a very similar thing. And there is a second order version. So this one, your input, your independent variable is this. So that's your x value. If you square it, you get the second order one, like so. And for that one, you also square that constant. So that's the main difference between these two things. Again, this part of the lecture notes is asking the same question: which one fits better given some data? Okay, so which model would you choose? Because then you can predict the rest of this. You can predict, beyond your data or in between your data, which is covered in this lecture. And notice that the two models we have, the first order one from the slide before and the squared second order one, has a crossing point, like so. Okay, so those are the two things you're trying to fit, and this is the data you have. So again, that's your x, that's your y. So you can use this linearization and use that to do a straight line least squares fit. So effectively, you have to adapt each of these into this form. Okay. So not that difficult. You just look at which part corresponds to which part, like that. So you got your this is your x value, so it becomes 1 over x. And you can see that it's actually the same format as your alpha. So alpha, your a in front is actually this, and your beta is that. So it's fairly straightforward. And for the second order one, it's these two things where that one's squared. That's the only difference. So if you rearrange it using this format, you get these two things here. Okay? So you can see that you got ks and other constant vm there. And for the second order one, the only difference is ks squared, and it's not x, it's x squared because it's second order. So you're just rearranging it to this form. You can actually do it without knowing that linearization rule. It just makes it easier because you don't have to derive it by hand. So that's just rearranging it to that format. And now what you have is you have your function value, your y values, and your x values, and your a0, a1. So you can use any linear regression method, such as polyfit, to fit a line to this data. Okay? So I'll show you the MATLAB code. So in this case, we're doing a straight to MATLAB thing instead of doing it by hand. Okay? So before going into the code, I'll recap roughly what polyfit and polyval does. Okay? So this is a very simple example. I'll go for it. You have, just say, a bunch of x values, and you have a function. I've done this here, so there's some noise to your y values. Okay? So it's x squared. 2x plus 3 plus some noise, so it's not exactly perfect. You then do a fit. So this is a straight line fit using polyfit, polynomial fit of your x data, your y data, and first order, so just up to x to the power of 1. And if you want to generate your results for each of those x values, you just use polyval. So you give it the output of polyfit, which is the model you fitted, in this case a straight line. You give it the x values you want to calculate the y fitted values for. So that's y-fit, and then I'm plotting both. So I'm plotting the raw data as blue dots, and then a straight line and red crosses for the fitted data. That's what this does. So that's what it looks like. You can see that if you zoom in a bit, the noise is not very strong here, but you can see that the fitted line is not exactly on the data because it's offset by the straight line, from the straight line a bit by noise, but this is how you use polyfit and polyval. So polyfit gives you the a0, a1, and so on in your polynomial function to do the straight line fit, and polyval lets you sub in an x value to that model. Okay. So with that in mind, the enzyme version uses the polyfit and polyval to make it a bit shorter. Okay. So let's start at the top. This is fairly long. This is the usual three things. This is your data from the lecture slides. Because of the way it's rearranged, recall that you have 1 over the independent variable, so that's your x. And this is the first model, so this is not the s squared model, just the s model. You have 1 over s and 1 over v as your sort of v is your reaction velocity, sorry. And you're fitting these two things to give you your first model's parameters, P1. So you're doing a straight line fit after linearization. Then to get back the Vm and Ks, you have to do the divide because it's 1 over. And for this, you're using Vm to get Ks because of the way the equations are arranged. And then you the final fitted value is just subbing in all these things, all these parameters, VM and KS, and your X values into the final equation. Okay? So the only tricky part here is that firstly, you're not fitting on the X and Y values directly, you're taking 1 over because of the linearization. You do the fit, and then these gives you your A0 and A1, but because your A0 and A1 represent things like 1 over VM, you have to get VM and KS back by dividing things over each other. If you're not sure about this, feel free to ask questions on discussion board afterwards, but effectively it's just doing the math you just saw on the slides. And the second part, the only difference, as I said, was that you have S squared, so your X values are now 1 over S squared, not 1 over S. And similarly, because KS is actually squared in your P values that are returned here, so in your constants that are returned, you have to take the square root to get back KS. And then this is, again, substituting in everything into your main equation. The rest of this is just plotting, so I'll show you what it looks like. So it gives you this code gives you 2 figures. This is the linearized version, so I'll show you this first. This one shows you the straight line least squares fit when you have taken 1 over V and 1 over S. And similarly, 1 over V versus 1 over S squared. So you can see that they fit, and from looking at this, it seems like the green, the second order model, fits better. But you can actually plot it back in the original and it makes it very clear. So if you plot it back in the original S versus V, which is what you want, so this was your dependent variable, your function, the second order model fits the data a lot better. Okay? So if you were to calculate the R squared and the errors and visually looking at it, it's better. And again, if you were to do it experimentally, just to confirm, you might take a few more data points to see whether it fits the green line. Okay? So that's how you choose between models. In this case, a saturation growth rate model. Okay. Any questions about this? Okay. Again, if you're not sure, feel free to ask after the lectures or on the discussion board. So that's fitting another nonlinear model by linearizing it. And in this case, the main difference from last lecture is that we're using the built-in polyfit to do it. And if you look down at the plotting code, there's a lot of labeling and things like that, but effectively the plotting uses polyval, which substitutes in your X values based on the model that's fitted to give you the Y values. So this is actually your Y fit from the example before. Okay. So these were the 2 things shown. Second order seems better. Now, we've shown you how to fit lines, and you can get a model out of it, and you can choose models, which is already quite useful, but there are other uses of it. And the issue at the moment is that with linear regression, you can only fit a straight line. So even in cases where you can't linearize your model by taking logs on both sides or rearranging the equation, it's a bit limited. So what you may want to do is do polynomial fitting, which I mentioned polyfit does. So a polynomial fit is effectively something like that, where these are all constants, okay? And this is a power. So if you have a third order polynomial, the biggest n value in the front is free. That's what the order means. Okay? So a 0th order polynomial is actually just a mean. So that's the worst state of, as I mentioned last time, it's the simplest model you can fit. So if you have polyfit xy0, it gives you back the mean of the data. Okay. So here are a few actual polyfit examples. If you have some X and Y data, this is what we've been doing so far. It gives you back a straight line fit. So that was your A1, A0 from before. If you put in a order free, it gives you back a model like that. So try to fit a third order cubic into your data, and this is the mean. Okay, instead of order, sometimes in the help files and also in math books, you'll see degree, which is similar. It's just the highest X power. So, with polyfit and polyval, you can actually do interpolation, which is something quite useful. So I'll quickly show you this. The idea here is that just say you have some data, like so, and you fit it, in this case, an X squared, a quadratic equation, like just say a parabola to the data, and you want to find out the Y value of the fitted model at that location. So normally you would have to find the equation, substitute in an X manually. But with polyval, you effectively just do this, as I showed earlier. So that's called, actually what you have been doing there is actually called interpolation, where the data, your X data, doesn't actually contain 3.5 as a value. So it may be something like X equals V, X equals 4 is like that, and you fitted a curve to it, and you're guessing the value of 3.5 at X equals 3.5 by the fitted curve. So that's another use of curve fitting, is you fit a model and then you guess between your data, and that's called interpolation. Okay? And that's quite useful if you need to know guess, and it's a lot better than just assuming a straight line, which is not that good if the distance is quite far. Okay? So here are some examples. Just say you have this data, and you first try the mean, which is like that, and it gives you this data. Okay? Now the reason why there's so many dots is that it's interpolating, using polyval to interpolate, to guess the values between, for all these x values. So x-inter are the x values you want to guess the function at. And it's between your start point, end point, so between the x value of that and that, but for 50 points, okay? Which is why the red line is so dense. Then you're calculating the y value by taking the fitted model, in this case a mean, and substituting in the x value into that model, which would just be the mean value because there's no x in the equation, and it gives you that line. Okay? So that's how you do interpolation graphically. You can also just save the value and use it for some other calculations. Now, if you fit something better than the mean, a straight line in this case, so that has changed to 1, you will get a straight line fit that's least squares fitted. And again, we're using 50 points, so these points are interpolated apart from the ones exactly on the data. Now you can go second order, and third order looks probably the best. There is a general rule which will be repeated later on. For data that you don't know where it comes from and you're just guessing the model for, a cubic, so you have a cubic where it starts with x to the power 3, is pretty much the limit of what you want to go up to. If you go too high power, you actually you can get issues which I'll show later on. So that's fitting, and there is the code for this is also available. So this is the very first version I showed, where you're fitting a single guess at 3.5. Okay, so those are the raw, that was the raw data. The red line was a second order fit, and you're using polyval to guess the value based on the fitted model to estimate the value. So that was the fit to give you a second order parabola, and you have a polyval to show the order. This line plots everything, and then you're saying I want to know what the function would be with the model at 3.5, and you're showing it as a green circle. Okay. And then the multiple order one is here, so I'll run that as well. That's quite large. Okay, so that's first order. Okay, second order, third order, which was where we got up to in the lecture slide. So you can keep going to as many orders as you want. But you notice that as you go higher orders, this is pretty much the best fit you can get, but it's n equals 5, which may not be your actual data. It could be due to noise that it fits so well. When you go higher and higher order, you notice this really strange excursions. So if you were to do interpolation between these two values, that's most likely quite off. Could be a factor of 10 off. Okay? And similarly, if you keep going higher, there's some things wrong there. So this phenomenon is called overfitting, where you have a ninth order polynomial and the number of points you have doesn't support that. Okay? So it will fit perfectly, but then it's a wrong model. Okay? Okay, so that's this example onwards. And that's the thing I just showed is what's called a hazard. In this case, a numerical methods hazard, but hazards in general just mean things where you're applying maths to a problem without understanding what's going on. In this case, the data we had 6 points, 0 to 5, steps of 1, you got 6 points, and you're fitting a fifth order polynomial to it, so it'll fit perfectly in this case. But you can see that if you were to interpolate between 0 and 1, you will have a value like that, which is doesn't look right, okay? Unless it happens that you're very lucky and the actual model looks like this, okay? Which is unusual. So as your degree of polynomial gets close to the amount of data you have, MATLAB will actually give you a warning when you use polyfit. So if you have 6 here, it will actually tell you that it's poorly constrained problem, ill-constrained problem. So that's why we recommend trying a cubic first, and later on you see that you can also, if a cubic doesn't fit properly, you can break your data into sets and fit cubics to them separately. But you don't want to fit a very high order polynomial because you're effectively overfitting because there is no error here, but it's not the model of the underlying physical system. Okay? So that's an interpolation hazard. And you can see other cases here where it looks like pretty much a parabola or another kind of model, maybe 2 exponentials either side. But if you were to do a very high order n squared, x to the power 5 or 6 fit, you get all these strange values. And if you were to just not look at it and use that as the model, it'll give you really strange results later on. Because for this range, it will still work sort of okay, but then when you go to this side, it will give you really strange values. Okay? So the main point behind this lecture and last lecture is to make sure that if you can plot the data and plot the fit and make sure it makes sense physically. Okay? So this stuff doesn't make sense because you're overfitting the data. And note that in these cases, the R-squared will tell you nothing because for the data points you have, it fits perfectly. So there's R-squared of 1 in this case. Okay? Any questions about interpolation hazards? Okay. So I mentioned cubic is pretty much the rule of thumb for most engineering applications for a guess of what model you want. That's the highest one you want to go. And if you want to go, if the data doesn't fit well, you can try it multiple curves. So this is an example. So this was an example actually from your labs where you're doing piecewise plotting in that case, but now I'm going to fit data to it. Okay? Fit a model to it, sorry. So that's what the data looked like. If you recall, that was the trajectory of the rocket. So that's the raw data. Okay? And if you try a single cubic, which is the advice I gave before, it doesn't fit very well. It'll give you relatively okay residual compared to a mean. Still better than a mean, but not much better. So let's try a 15-order polynomial, which is the hazard I mentioned. Not a good idea. It fits pretty well. The residual will be quite small, but you can tell it's unlikely for a polynomial to have an x to the 15 rule governing how. It's unlikely for a rocket to have an x to the 15 rule governing how it operates. Okay, so in this case, you may actually decide, there are 4 stages or 3 stages to the thing, like so, and then a drop off. So if you were to do 5 cubics separately, you actually get a fairly good fit. Now this part is still a bit off, so it's actually an exponential, as you know from the raw data. But in this case, I'm assuming that I don't have this maths, I just got the raw data, and I want to fit models to it. Okay, that's the assumption in this case. So you can see that if you break the data up correctly at these points, in these segments, you actually can fit individual curves to it, and cubics work most of the time. If you knew a bit about how this part works mathematically, you may choose an exponential, which will fit perfectly. Okay? So that's what we mean by using cubics as a first guess, but then you can break up the curves into separate parts and fit it a part at a time. Okay, I'll show you this in code. Okay, I'll ignore this for now, this one. So this is quite long code, but most of it's just repetitious. The very first one I showed was single cubic, so you have fit the T and B data generated as you did in the labs, but we're assuming we don't know what the model is behind this data. So if you were to measure it directly, it might look like that. You then have your T and V values and your cubic, okay, for polyfit, and I'm just plotting it for all the T values that I have. Okay? And this is the 15th order polynomial, 15, same thing. And finally, we're trying it in 5 segments, so I've got 5 sets of data. Okay? And then fitting 5 times, polyfit. So these are 5 sets of cubic, A2, A1, A0s, that sort of thing. And you have the plot 5 times. So I'll run this. Okay, so notice that for the n equals 15, it gave you a warning that is ill-conditioned, which is good of MATLAB. But you can see that this was the n equals 15. It works, but it doesn't work very well for this part because you're assuming one curve. This was a really poor single fit, and this was the one where I broke it into 5 segments. So the code for this is available online. But effectively, just to repeat, I'm taking that chunk, fitting a cubic, taking the red one, fitting a cubic, and so on. So in practice, what you would do in a situation like this is if you have some data that looks very piecewise, let's quiet down a bit. So if you have some data that looks like it's very jagged, usually the jagged part is due to the fact that at that stage, the physical system changed models. So in this case, it's changed models. So what you want to do is basically take those corner points and specify that as a segment and just fit the data for those x values. Okay. Now, as I said, this doesn't fit very well because this is actually an exponential underneath. But it's good enough as a first guess, and then you can refine it afterwards. But you can pretty much say, these things before looks like it fits well enough. I can focus on improving this. Any questions about piecewise curve fitting? Okay, that's pretty quick. So, now, extrapolation is a lot worse and more dangerous than interpolation. And extrapolation is actually, unfortunately, what a lot of news does when they report on engineering and science stories. So let's say you have 3 data points, okay, like so, from a curve, and the underlying model is supposed to be this, the blue one, supposed to be a blue one. You do interpolation, it's hard to go wrong unless you overfit, because you're saying, I want values between these things and these things, so it's unlikely to go outside this range a lot. Okay? Extrapolation is guessing, estimating values outside your range of x's that you've fitted the model for. So if you were to fit something that is like so, and that's your fit, it still gives you an okay guess for the actual black model that you have there. But if you don't fit the correct model with these data points and you extrapolate, you can say that something will be 0 by the year 2050, okay? Which is what happens a lot with mathematical models that you get reported on the news. So extrapolation is dangerous unless you already know a lot about the model, and it's usually better just to, if you can, to take an actual experimental data point there, and you will then correct it because the fit doesn't fit, okay? So just to repeat, extrapolation is dangerous unless you know the model. And here is an example. This is actually originally from a news report in the States, where they basically only showed up to this point. I think this is quite an old news report. And what the author did for this book was say, okay, if you take this model forward, what happens? So the guy said claimed his model is really accurate, which it is, because up to that point it's really accurate, and because it fits all the data perfectly. But if you were to extrapolate it further, it suggests a really big calamity in the year 2000. This is because there's a 7th order fit to not enough data. Okay, so that's the problem with extrapolation. Okay, so we've covered very, very briefly just this material. Now I go on to the assignment. Don't groan. This one's not too difficult, actually. Hopefully. So quiet down, and I'll stay around a bit longer because this is the last lecture before when the assignment is released this week. This is the last lecture until the week after the break, so you can ask questions about this as well. This is not online yet, just to repeat, but what will happen is on Blackboard there will be a folder called assignment. There will be a separate discussion board where you guys can talk about the assignment, as long as you don't give full solutions. I'm fine with that. And the due date is end of week 11. It's quite a long time away, but you should definitely get started on it to see how long it will take. Late submissions allowed, but at a fairly substantial penalty on the Monday the week after. Okay, now given that this is a programming assignment, there's usually a lot of questions about copying. The general rule is you're allowed to work together in a group as long as you acknowledge who you're working with. Okay, that's the same in industry. If you worked with 10 people and then claim you did all the work, you get into trouble. Okay, so, and the fact is this is good practice for you later years, so I would highly recommend you doing it yourself. What you'll be given is a zip file with all the assignment code in it, but it's all blank. You have to fill in the rest. You have code sort of M files named as question 1A, so on. And there is a file called run all, which will run to check that your assignment works properly. So you should not modify this file, because that's the file we'll run. And that will run all your code. And so if you can't do a task, just leave that task blank and we'll know about it. Okay? So you'll be given a zip file with the data, and you just unzip it into a folder and you start filling in the code in that file. And when you submit it, you zip it back together. There will be instructions for that, and you can put it onto Blackboard. So the entire assignment process happens on Blackboard, including submission. And there are some submission details there I won't cover now. Okay, and assignment marking is fairly straightforward. It's 10, as mentioned in the unit guide, it's 10%, 1 mark for 1%. The main thing to note is that when we run your code, everything should happen automatically. So there are parts of the assignment where you need to read in files. The person marking it shouldn't have to enter your file names and that sort of stuff. It should happen automatically. So by default, all the data will be in the same folder as your code, so don't move them around. If you just read the data in with the file name as the input, it should work properly. Okay? And if you want to check whether you've submitted it correctly, you can zip it out and then basically submit it, and you're allowed to take back the assignment, so do that early. You can download the zip file, unzip it, and see if everything runs. So we're going to do the same thing as like that. We'll just download the assignment, run the run all, and everything that outputs would be your marking. Oh, yep.
Do you use marks for collaborating?
No, but if you collaborate with 20 people and produce the same result as someone who's worked solo, then there will be a difference in marks. So that's the way it works. Now, this assignment is fairly simple. So if you find yourself collaborating a lot, that's not a good idea for later years, actually, when you have to work solo. Now, there will be, as I mentioned, there is a discussion board on Blackboard. There are some hints in the template M file as to what you should do for each task, and during the lectures I may provide some additional hints as well. But most of it's already there. So, okay, question 1. This is my question. So, let's quiet down a bit. This is actually in my office. This is a Kinect, for those of you that play games, and it's pointed at a corner of a room. Now, the thing is, this thing actually has something called a depth camera in it, so it gives you 3D information. That's how it works. So, with some code, you can actually get the 3D depth out without the Xbox, and this is what I've done. So, I've measured the 3D points for this corner, door handle, and this image doesn't show up because it's flat against the door. So this is the view of the sensor, and this kind of depth sensors, the more accurate ones, are used in industry all the time, especially for manufacturing automation, where you want to measure something physically in size. And it's also used for motion capture in film studios. So we've given you this data, and I've played around with it a bit, so it's a bit easier to read into MATLAB. It's just free text files, X, Y, Z. Okay? And each of them are the X and Y and Z 3D coordinates of each point in this image. So the image is 640 by 480 pixels, but each pixel is X, Y, Z, not a RGB, red, green, blue valley. So the goal of this question has 4 parts. Okay? First part is just plot the data. So you load the data in and you plot it. It should be fairly simple. There is a hint here where this word actually gives you some hint as to what function you should use. And you just plot it using that. So it's fairly simple. Now the thing to note here, I say you're plotting every 10th pixel, so that's not a 10th of the pixels, is really much a 100th of the pixels, because you're plotting every 10th pixel in the row and columns. Because you can imagine a 640 by 480 image, if you plot that in MATLAB in 3D, that's a lot of points. So if you take every 10th pixel this way and take every 10th pixel this way, it's sort of a sparse 3D grid. So you will see this image in 3D, so 2 walls and a door handle. Okay? So that's the first part. The second part is you have taken these 3D points of the corner and you just ignore the Y dimension and you just average everything down this way. Okay? So if you were to get this in 3D, it will look like sort of an L shape if you were to look at it from the top down, because it's a floor plan. Okay? So if you average every single column this way, you will get effectively an L shape that represents this wall and this wall if it was on the ground, like a floor plan. So that's the second part. Should be fairly straightforward. You have to draw it and make sure it's correct. Then the third part is you do the curve fitting I just mentioned, the piecewise curve fitting I just covered with straight lines, and you find the walls, okay, automatically. The only thing you have to do manually is figure out, as I said before, where the segments join, where the corner is. So you can see that physically on the curve from part B. So after that, you have the walls and you have all the data. The last part is the tricky part, where you have to then fit that wall to every single column of pixels. So what you've done is you've found the wall, the sort of blueprint of the room along here. Then you're saying, okay, now if I take back the original 640 by 480 3D points, and I fit to each row the 2 walls, which doesn't belong? What doesn't belong to the wall? Well, the door handle shouldn't belong to the wall because it doesn't fit well. There's a big error. So at the end, what you get is an image that shows you where the door handle is. Okay? So it's all automatic. So if you follow those steps, that's what you get at the end, which is basically an image that's roughly looking like that, but door handle is highlighted. And there is more details in the task. Now, it seems quite complicated, but if you do one step at a time, it shouldn't be too bad. This takes about 30 minutes when I do it. So I multiplied it by quite a bit. Yeah. So you can see the factor I've used for multiplying this. It's quite a bit. It's quite down. Okay. So the second task is set kindly by the Sunway lecturer, and is similar but a bit different. Now the second question, the second question task D and E in it you won't be able to do until after the break unless you read ahead. So keep that in mind. But it's fairly simple stuff. This one's a bit more wordy because there are more steps involved, but it's similar difficulty. Again, you get given some data, and the arrow C is actually a C that got disappeared over time because the water was diverted from it. So that's what it looked like quite a while ago and more recently. So the goal here is to figure out when it will disappear completely, which sounds like something hopefully that you know about from last week's lectures. And you have been given some data, and it's basically the surface area, but it's the change in surface area because it's easier to measure that way. You've been given initial values, so if you look up numerical integration, which is next week after the break, or you can just look up the lecture notes, there are examples of this, and there's a hint as to what function you may want to use. It will give you the actual surface area of the lake over time. So that's the first task. The second task is a bit difficult, task B, but that task is independent of all the other tasks. So if you find it difficult, you can actually skip ahead to the other ones because that's only used to check part A. Okay? And that one, you get given a bunch of aerial images, and it tells you what functions to use in MATLAB, and you can remove everything that's not to see and count how many pixels there are using MATLAB. And that should correlate with what you got from part A. Okay? Then the rest of this is just model fitting. This one you've just done, polynomial model, second order. So that shouldn't be too bad. You fit the model, and you have a look at to see when they will head to zero visually. This thing here is the thing I mentioned where you won't learn until after the break, but you can read ahead about ODEs. And finally, you're just saying, is this model better or is this model better? Okay? Now, that's 9 marks total. So we expect a bit of work because you have 9%, which is a lot more than your labs. But there's also going to be 1 mark left at the end, which is only given if all your code is done completely properly. Okay? So that's the mark that separates the top students. The coding style and comments basically refer to whether your code is clear and easy to understand, well documented, and also runs properly throughout, so we don't have to modify to get it working. So that is the assignment. I'll try to upload it as soon as possible in the afternoon. If not, it'll be tomorrow morning. Any questions, feel free to come down and ask. Otherwise,